safe side. Those of you that are attending in by Zoom, so today's lecture and Friday's lecture, I'll be using a lot the board behind me. We will be doing a lot of calculation related to next week's lab. So if you want to see the board behind me clearly, what I will do is I'll stop sharing my screen from the PowerPoint when I want to use the back, the, the board, and you want to change your view. If you go way up to the top, to the far right corner, there is a view icon. If you click on it, you select speaker view, then my screen will be big on your screen. Okay, so you just do that. All right. If you have any questions, I might not be paying attention to the chat, but please do ask your question. We'll have Rachel keep an eye on the chat and let me know if you have questions. And also for participation, use the chat. I might not be looking at it, but if there's a question or an answer that needs to be discussed, Rachel will let me know. Okay, let's get started. So what I decided to do, since I need to make sure we're we're 2 lectures behind. So what I'm doing right now is I'm starting the reagents and buffers lecture. And I'm just skipping one lecture for now, which is sampling and sample preparation. We'll cover that next week. Today and Friday, I'll talk about preparation of reagents and buffers because that's the subject of your lab next week. And there's a lot of calculations that I want to refresh your memory and have you practice with me today and Friday so that you are ready for the lab that has a lot of calculations next week. What I ask you to do, all of you, pull out a piece of paper. Those of you that are attending virtually too, pull out a piece of paper that is big enough for calculations. You're going to be doing calculations alongside with me today and Friday. And then on Friday, I'll have Laura put up an extra credit assignment for you where you take a picture front and back if you used front and back sides of your paper. And it's for +5, not +2, +5. There are going to be a lot of calculations. So Al and Aaron, right? Yeah, okay. So there will be a lot of calculations that you might need 2 pages. Make sure you take picture of both the complete calculations, not just the answers. And then you would just upload that for the +5. This is optional, but I encourage you to do it first for the experience and exercise, second for the extra credit that will come in handy throughout the semester. Okay. So I will start sharing my screen. Okay. And oh, it's doing this again. So how did you flip them, Rachel? When to share? Oh, you see that? Okay, good. All right. Okay. So why is it important to go over reagents and buffers preparation? This is not a chapter in your book, so but you'll find 2 chapters about preparation of reagents and dilutions and concentrations in your lab manual. And that these would be chapter 2 and 3, I believe, in your lab manual. So why is it important? Because as an analyst, whether you're working in a research lab or whether you work later on in industry and you happen to work in a lab, you would need to prepare reagents and sometimes buffers. So you need to know how to prepare them, and that requires some understanding of concentrations and the calculation that goes into preparation of these reagents. And not just preparing, knowing the calculations, and then how do we prepare them? How do we bring up to volume, to a certain concentration, to achieve a certain concentration? How do we check the pH of our buffer? How do we adjust the pH? So you will be needing to learn the calculations or remember these calculations from your general chemistry classes, and then apply them to prepare the agents and buffers. So, and here we go. Let's try to remember what we know about buffers. So the following is true about a buffer. Consists of a mixture of weak acids and their conjugate base, has a neutral pH, stabilizes a certain pH. Chrissy, you want to give it a go? Chrissy goes with F. Okay. Any similar or different answers? People are nodding. And okay. So you're agreeing that it is F, and I am agreeing with you. It's A and C. So conjugate base is basically when a weak acid or an organic acid dissociates. That means it gives up its hydrogen, it becomes a salt or a conjugate base. Okay, so the dissociated acid is your conjugate base. So that has multiple names. Dissociated acid or the salt means conjugate base. The weak acid is the not dissociated or the undissociated form of your acid that has the H attached to it, the proton attached to it. So that these are terms that you want to know because they might come across with you, but sometimes we say conjugate base, sometimes we say dissociated acid, but that means the same thing. Sometimes we say salt. So it means they mean the same thing. Of course, buffers have a range of pH. We have acidic buffers, we have neutral buffers, we have basic buffers. So it's not really necessary a buffer is at the neutral pH. But the most important job of a buffer is to stabilize a pH. So if you're running a reaction and you want to make sure that your reaction is maintained at a particular pH, you need a buffer. So that if the reaction goes forward, it might become acidic or might become basic and won't be suitable for the reaction to continue. So a buffer will maintain a specific pH regardless of the reaction that is happening. And oftentimes we need that. Okay. So here's some general chem revision. You're going to be hearing and using a lot of molarity, normality, number of moles, mass, molecular weight. So we need to remember how to use them and when to use them. So molarity, oftentimes you have to prepare concentration at a specific molarity. So you need, and you have a mass, you have, not a mass, you have a solid powder, and you want to take a certain weight out of that powder, put a certain amount of water to get to a certain molarity. In order to know how much to weigh, you really need to know the relationship between the mass, the molecular weight, the number of moles, and the molarity. So hence, you need to remember molarity for number of moles of solute per 1 liter of solution. And number of moles is equal to mass by the molecular weight of your compound. So you will need that. You will be using it a lot, these equations. Sometimes you're given a normality instead of a molarity. And normality is related to molarity by the number of moles equivalent of a solute. What does that mean? If we have acid or base, the number of mole equivalents are of those that are being exchanged during the reaction. So protons are being exchanged and hydroxyl groups are being exchanged in an acid-base reaction. So let's look at this example. If you have H2SO4, that means you have two H's. So two protons are being exchanged in a reaction. So then H2SO4 has two equivalent number of moles equivalent. So 1 molar of H2SO4 is equal to 2 normal because normality equals X times molarity. X is the number of moles equivalent. If you have HCl, you have 1H, so molarity equal normality because molarity will be equal X, which is 1 in this case, times the molarity, and that would be same. Same with NOH. NOH, you have 1 OH, so the X is 1. Calcium hydroxide, you have 2 OHs, so the X is 2. Equivalent weight is important, and that will come in when we talk about titratable acidity later on in the semester, where you're determining percent acidity or percent titratable acidity of organic acid in juices, for example. So a lot of organic acid has more than one carboxyl groups. That means it has multiple H's. So when we want to determine the percent, we have to account for those multiple H's. So in the equation, instead of using molecular weight, we use equivalent weight to correct for the number of H's that are exchanged in the titration reaction. Okay, so that's why it's important to remember equivalent weight is molecular weight divided by the number of moles of equivalent. It will come later on in the semester where it will make sense. Oh, we need the equivalent weight. Percent concentration. So here in this case, it is per 100 units. So you have, it can be weight by volume, so grams per 100 milliliters, or it can be volume by volume, milliliters per 100 milliliters. So yeah, so you will sometimes get to prepare a concentration in percentage or use a concentration of a percentage that you need to convert to molar. So that's why percentage is important. Also, concentration can come in parts per million, for example, or parts per billion or parts per trillion. And this is relevant when your concentration is very, very small, much smaller than 1%. Then it doesn't make sense to report it in percentage. Then you would report it in the next smaller unit, which is parts per million or milligrams per kilograms or micrograms per milliliter. It's the same. And this is, for example, relevant when we do HPLC. For example, your concentration will be micrograms per milliliter. They will be in ppm. If you're doing GC, sometimes your concentration can be parts per billion because it's a very sensitive equipment. You get concentration as low as parts per billion and sometimes parts per trillion if you're working with MS type of analytical unit where it really is very sensitive. Okay. Equation of neutralization. This is very important, not only for acid-base reaction, but also for dilution reaction or preparing dilution reaction, where you prepare a diluted solution from a concentrated solution. You will need to be using that equation. So what is it really, equation of neutralization? It's merely equivalent of one reactant to equals merely equivalent of the other reactant at equilibrium. So at equilibrium, the concentration times volume of one would be equal to the concentration times volume of the other. Oftentimes, the concentration is in a normality or a molarity. It can be any unit, really. If we're doing dilution, the concentration can be in any unit. And then your volume would be in milliliters. So X milliliters times concentration equals X milliliter of the other reagent times the concentration of that reagent. So like I said, this can be used in dilution protocols and you will be using it a lot. So sometimes you have to prepare a diluted solution, let's say 0.1 normal HCl from a 12 normal HCl. You'll be doing that in lab next week. So the bottle comes very concentrated, and then you need to take specific volume out of that and mix it with water to produce a liter of a much concentrated, much diluted solution, like a 0.1 normal HCl. So that would be your first thing on your piece of paper right now. Prepare 1 liter of 0.1 normal HCl from 12 normal HCl stock solution. Using that equation, how many milliliters of the 12 normal HCl I would need to put with water to get to a 1 liter solution of 0.1 normal HCl. Please do the math. And let me know when you're ready. It'll take a couple of minutes here. And when you're ready with an answer, you can give it. Anybody with an answer? Yes, 8.33 milliliters. Okay, so here's how we do it. So it is X milliliter. That means how many milliliters of 12 normal HCl I need to take out of that concentrated bottle and put it in a volumetric flask that is 1,000 liter to generate a 0.1 normal HCl. So the concentration we're after is 0.1 normal HCl, and the final volume we're after is 1 liter, 1,000 ml. And then the concentration we currently have is 12 normal HCl, and we were solving for how much we want to take out. We just do your algebra here to solve for X, and then make sure you have your units correct, and then you end up with 8.33 milliliter. Great, so you got that volume. Now what? You're in the lab, then you get your volumetric flask, you put in it some water because you don't pour water over acid, you pour acid over water. So you put a little bit of water so that splashing safely. So you put a little bit of water, your acid, and then you make up to your volume to that one liter mark. Okay, so if I ask you in a test, how do you prepare 0.1 normal HCl? You don't just give me the calculation, you give me the calculation and then you tell me how you prepare it physically in the lab. You take this 8.3 ml, yes. Oh, don't ask me about significant figures here. All right, so the significant figures here is dependent on the tool you've used to withdraw your volume. So it depends if you used a mechanical pipette or if you used a graduated pipette, you want to see what the accuracy of it. So the pipette would have written on it, it's accurate to what decimal point. That would be your significance figures. If I don't give you that in a test, in a quiz, don't worry about it. So, yeah. Let's do some other type of calculation. Calculate the number of moles of calcium in 25 grams of calcium chloride 2 hydrate. So, what you need to know here, you need to know the molecular weight of this molecule. And in order to determine the molecular weight, you need to know the molecular weight of each of these elements. So calcium, who remembers what the molecular weight of calcium? It's 40. So calcium has a 40 grams per mole. Chloride, anybody? 35.5 grams per mole. Hydrogen is 1 grams per mole. And oxygen is 16. All right, give it a go. Yes. Oh, no, I'll give one. Yeah. I will give you the molecular weights in an exam or a quiz. Yeah. Okay, let's solve this together. I don't remember what it is. My other screen is covered up, but let's do the math together. Maybe I will stop sharing for a second and then put me on speaker view so that you will see. Okay, so the molecular weight, the total molecular weight. So I have two chlorides, so that means it's 71. And then I have 1 calcium, that is 40. And then I have 4 hydrogens, and I have 1 oxygen. So that's basically 131, right? Or 1, what's that? What am I off? 12, 121, right? 131, what am I? Oh, 2 oxygen, sorry. I'm not hearing very well. Okay, 32, so this would be 147, right? Okay, so I have 147 grams per mole as my molecular weight. So a number of moles equals mass over molecular weight. And I have 25 grams over 147 grams per mole. And then my answer would be something moles. So I'll share my screen again. 0.17 moles. Okay. All right. This is something that you will be preparing. You will be preparing NOH. Let me see, that's pH and technical acidity. You won't be physically preparing because that's after Thanksgiving. So anyway, let's practice how to prepare 1 liter of 0.2 molar NOH. Yeah. Okay. All right. Yes. So we have two different solutions, 3 molar NaOH and 45% weight by volume NaOH. Let's tackle the first one first. Oh, and you might leave the molecular weight of NaOH. The molecular weight is 3, with sodium is 23 grams per mole, and then the hydrogen is still 1 gram. And we need 3 molar, we have 3 molar, and we have 45% anyway. And we want 1 liter of 0.2 molar. So I'm going to stop sharing my screen. What's that? Okay, I saw something coming. Is that what they said in the chat? Okay. All right. Do we have at least the first one from 3 molar? What would be the answer? Yes. 66.6. Let me see my answer here really quick. Where am I? Yes. So let's solve the first one together. All right, so we have 3 molar, so you apply the molarity times X milliliter, that's what we're trying to solve. How much from the concentrated solution we need to prepare 1 liter, which is 1,000 milliliters, times 0.2 molar. So you solve for X, it is 6.7 milliliters. Okay, is that clear? That's easy, right? Am I frozen? by any chance? No? Okay. Let's do the next one. I don't know why my screen is doing this on the file. I have no idea. Okay. So for the next one, the first thing you want to do is you want to unify your units. You want to see, okay, what am I looking for here? I want in molarity. I want a concentration in molarity, and I have a concentration in percentage. So I want to take this percentage and convert 45% to a molarity. So I need to determine what's the molarity of a 45% solution. That's the first thing you want to do. Is your 45% NaOH, what would it be in molarity? So convert that as a first step and let me know what you get. Okay, anybody with a molarity? Anybody in the chat? Are we stuck? Huh? Potentially. Let's solve it together. Okay. So when we say we have, okay, I'm gonna get the molecular weight here really quick. 23, 24, 16, that's 40. Okay, so we have 40 grams per mole as molecular weight. Ah, okay, 40 grams per mole molecular weight of NaOH. That's the first thing you want to get. Then you want to say 45% is 45 grams in 100 milliliters. That's what this means. 45 grams per 100 ml is your 45% NaOH. And you want to remember that in number of moles and molarity, they're in liter. So the volume is a liter. So here you have 45 grams in 100 ml. Then the first thing you want to say, how many grams I have in a liter? So 45 grams in 100, that means 450 grams in a liter. So you just multiply by 10 because a liter is greater by 10 than 100 ml. So you go, okay, so I have 450 grams per 1000 ml. That is my concentration. 45% translates to 450 grams per liter. Okay, so if I want to get the molarity, I need to know the number of moles, which is equal to the mass, which I have here, over the molecular weight, which is 40. So 450 grams over 40 grams per mole will give you, is that the number 11.25? Okay. So that would be your molarity. Now we have units that are the same, equal-units. So now I can do my equation, which is x milliliter of 11.25 molar. How much of this concentrated solution I need to prepare 1 liter of a 0.2 molar solution. Then I'll get my x, which is 200 over 11.25. What is it? $17.8 milliliters. So I will take that 17.8 milliliters, get the volumetric flask, put a little bit of water, my 17.8 milliliter, and make up to volume. Okay. Am I sharing the right one? Okay. Huh? We have a question? Hi, Sam.
We also does instead of calculating molarity, if we calculate the amount of grams in 1 liter, 2 molar, and then 9 grams in 45% volume.
So, but you already have your sample in solution. So you already have a solution. You don't have grams. You don't have a solid.
Okay.
So I'm already telling you to prepare it from a solution. If I'm telling you to prepare it from a powder anyway, then you would want to know how much you want to weigh out of that powder to get to that particular molarity, which you can do. But if your stock solution is the solution, you just have to do it that way. Does it make sense? Okay, good. Any questions? This is the time to ask, and don't be shy. We're all this. I know you've gone through this in chemistry, but it's been a while. Any questions on the chat? No? Okay, good. Okay. Sometimes you buy an acid that is very, very concentrated. And they tell you the concentration on the bottle as a percentage of volume by volume, not weight by volume. So for example, when we purchase H2SO4 sulfuric acid, the bottle comes in and it says 98% volume by volume, and it gives you the density on the bottle of the H2SO4. So you have the density and you have volume. Okay. Or percentage by volume. So you want to prepare 500 milliliter of 0.1 molar H2SO4 from this concentrated bottle. So I have a percentage. So what is the first step I want to do? We just did it in the previous example of the percentage. What did we do with the percent? Convert it to molarity. That's your first step. So, okay, so now you know that the first step is converting it to molarity, so I have equal units. So how do I convert 98% weight volume? not weight by volume, volume by volume, to molarity. So that is the first thing. And I gave you the molecular weight, and there is this density. What do I need the density for? You need to convert volume to mass, because you need the mass to calculate the molarity. So that's the first step. Go ahead. Did anybody get to the percentage in weight by volume so far? Okay, Kat, what do you have? Oh, the final molarity. Good. What's the final molarity? Sounds correct to me. Let's do it together. All right. So 98 milliliters per 100 ml. That's the concentration you have. Okay. So I want to convert volume to grams. So your density equals mass over volume. I'm given the density as 1.84 grams per milliliter. And then I'm solving for the mass, and I have 98 milliliters. So what is the mass here? 98 times 1.84. What do you have? Let's say 180 grams per 100 milliliters. Great, so now I have that. Again, same with the previous example. I have 100 grams per 100 ml. That means I have 1800 grams in 1 liter. So 1800 grams in 1 liter. Just times 10 here and here. Okay, so now I know that this is the grams and I have the molecular weight. I can get the number of moles, which is mass, 180 grams. Oh, sorry, 1,800 grams over 98 grams per mole. That's the molecular weight. Okay, so the mass over molecular weight, then I get 1 or 18.4, right? 18.4 moles, which would give me 18.4 moles per liter, which is 18.4 molar. So now I have units. So now I need from this, I need to prepare 0.1 molar H2SO4 and 500 ml of that. So then I apply again my equation, M by V equal M by V. We're solving for X milliliter of the concentrated solution. I want to prepare, not 1 liter in this case, I want to prepare 500 ml. And then I need a 0.1 molar. Perfect. Then I'm solving for X. So it's 50 over 18.4. That's molar. That's ml. Okay, so 50 by 18, 2.7. So I take this time a 500 milliliter volumetric flask. I put a little bit of water, I add my NaOH, and I make up to volume. Am I sharing the right screen? So that's exactly what I just solved here for you. And we got the 2.7 milliliters answer. This is a dilution problem. I will not start it, but if you want to think about it at home, that would be good starting to think about it because we will be doing a lot of dilutions. And then we can start with that on Friday and then move on to buffers. Okay, work on it and then we'll discuss it on Friday. Thank you all.